right? The piecewise function looks very different than the functions you've dealt with in the past. Piecewise function, there's our function notation, f of x equals, and then there's going to be this big script bracket, only one of them though. We've got this script bracket, and what that's telling us is, okay, there's going to be multiple rows here, multiple pieces in this piecewise function. Each row just corresponds to one piece in the piecewise function. So let's look at this one as an example, and then we'll kind of think back to that parachute example and think about how we could set this up. So what's this telling us here? This says f of x is equal to the top piece, the red piece, whenever x is less than or equal to -2. So for those x values, this is the function that we're going to graph, y equals 2x. Okay, that's a line, right? Line with a slope of 2, y-intercept of 0. What about when x changes, when x all of a sudden is not less than or equal to -2, when it's greater than -2, we flip into the blue piece of the function. Okay, that's where the equation that describes this piece is y equals -1 minus x. And that's the piece that's going to exist whenever x is between -2 and +4. Okay, when x is greater than -2 and less than 4, we're on the blue piece. And then again, when let's imagine an ant is walking on this function from left to right. When the ant's x coordinate is less than or equal to -2, he's walking on the red line. When his x coordinates are between -2 and -4, he's walking on the blue piece. But as soon as he steps on +4 and moves further to the right, when x is greater than or equal to 4, now he jumps to the green function. So what's that going to look like? Literally, it's going to look like 3 separate pieces that correspond to different graphs, different lines. Okay, we could do something like that with our example here. How many pieces would our piecewise function have to describe this adventure we just had? Got to have 5, right? Now, if I were to graph this thing, what would be, like we were using, I guess maybe there was even one more there. What did I have? Oh, piecewise function, yeah. Piecewise function just made up 2 or more function pieces, each with its own domain. So we were graphing, in this case, looks like a regular math graph in the xy plane. The input variable is what for this function? It's x. How do you know? How can you look at it and immediately know the input variable is x? Yeah, look right here. Because it's telling us f of x, right? That's function notation. And we'll go back and talk way more about function notation soon. But you guys have seen this. That tells us what's the variable we're inputting into the function to calculate an output, right? So our input variable is x. Our output variable is y. Remember, f of x is just a fancy name for y. I'm sure you've heard that before. For our previous example with the parachute, what do you think our input variable is going to be? What's determining here when we change from one chapter to the next? It could maybe be height. That's one way we could do it. What's another way? Time. Yeah, we could do time, right? We know how long we're doing each of these 3 parts, okay? The first chapter takes an hour, second chapter takes 12 seconds, third chapter takes a minute, and so on. What would the output probably be? What's interesting about this? What's the height? Yeah, the altitude's probably the output, right? So if I were to graph this thing, if I were to graph that piecewise function, it's going to look like something like that, right? Where we've got height in feet, I guess, and our input is time. And we could do that in, how about in seconds, I guess. It's going to be, times are pretty different. But what's this thing going to look like? Well, we're going to start off, I mean, we don't have to graph the whole thing, but we start off this first part where we're writing upward. It takes a long time. It's very slow. What's that going to look like? I start at 0, my height, right? And what do I do? Yeah, I just go up pretty slowly, don't I? Right? So as time passes, my height is increasing. I'm just going to go up like that, right? Eventually, I get to my highest point, which is 15,000 feet. And then what did I do? Well, let's see, then I bailed out, right? So I accelerate downward for a very short period of time. So that's going to be, what do you think that's going to look like? Okay, yeah, it's going to be close to straight down, isn't it? We're going to do something like, oops, I need green. Green, I said. Didn't order that color. Something like that. I'm picking up speed. It's getting steeper and steeper, right? The slope of this thing. Until I hit my terminal velocity, and then that's blue, right? I hit terminal velocity and I fall for a while. So now I turn blue. I'm going to go down pretty steeply for a while until I get to 3,000 feet, and then what happens? Okay, yeah, then I'm going to slow down really suddenly. What color was that? That was that, whatever that color is. We'll call it orange, close enough to orange, right? So then this thing is going to lose speed pretty quickly. And then the last step, I'm just floating to the ground at very slow speed. So it just continues on until I get to the ground. Right? That's what the graph of that piecewise function might look like. There are 5 distinct parts of that. And if we wanted to build that as a piecewise function, we would probably do something like that. F of t equals, I need to make room for 5 rows. And I don't know what the equations are here. We could figure some of this out, but that's really not the issue right now. We'll just call this first one equation 1. When is that happening? What's my domain going to be, right? The domain is the set of all the input values. You guys remember domain and range stuff? Okay, and we'll come back and talk more about that later. Again, that's kind of like next unit. We'll spend a lot of time on functions. But the values of x where this is happening are when t is greater than or equal to 0, right? Because we start at 0. And when did it end? After an hour. So we're going clear up. If that's in seconds, that's what's 3,600. So there's step 1, right? Step 2, we would have equation number 2. And the domain of that would be when t is greater than, we'll make that equal, greater than 3,600 and less than or equal to, what, how long did that last? 12 seconds, so 3,612, right? You see what I'm doing here? And we're just going to build this thing up so as t progresses, the ant's going to move from the red part of the graph to the green part of the graph to the blue part of the graph, etc. And we can just build the function that way. And it's what's great about this is this kind of function then, even though these are really different behaviors, we have a single function that can deal with all that at the same time. Okay, so let's go to a math one that's maybe a little simpler. Let's graph this thing. Okay, how could we graph this thing? What do you think? There's 3 parts. Suggestions. What would you do? And you probably can put the pieces together here. Any ideas? Remember, the red piece only exists in its domain. So where do I graph the red piece again for what x values? Less than or equal to -2. Okay, so then maybe we want to put some boundaries in here, right, to help us recognize when we're transitioning between the different pieces of this piecewise function. So one of those transitions is at -2, the other one would be at 4, right? So there's our vertical lines that are just going to separate the pieces of our piecewise function. The first one is going to be the red region, right? There's the place, every place to the left of this vertical line, that's the region where we're going to be graphing the red piece of the function. So now all we have to do now is just graph the red piece in that region. So how could we do that? We're just graphing the line y equals 2x because that's the piece that exists in the red region. I can graph that a bunch of different ways. We could use slope-intercept form, right? What's inconvenient about using slope-intercept form here? Like if I used mx plus b, the y-intercept is 0, right? And the slope is 2. That's maybe not the most convenient way to graph that line. How come? Say it again. Well, okay, like if I was going to use slope intercept form, my y-intercept is at 0, right? And my slope is 2. So I get a point there. Well, yeah, those points define the line. Yeah, but they're not in the correct region, right? So if I'm going to do it that way, I would have to take this line and kind of draw it, go backwards, and then erase a part of it. Whoops. Erase the part of it that's not in the red region. That's not very efficient, right? We don't really want to do it that way. So what could we do instead? A point requires how many, or sorry, a line requires how many points to graph? 2. So I only need 2 points. So what would be a more convenient way to get 2 points out of this? Yeah, just plug in values that are convenient. I'm going to plug in x values that are in the domain of the red piece, meaning in the red region, right? So I could pick any values less than -2. Now I'm going to suggest that one of them is a particularly good choice to pick. What would that be? And this is not anything mathematical. I'm just thinking about like common sense problem solving stuff here. What would be probably a really important value to plug in for x? -2 would be great because we want to know where this thing ends at the edge of its region, right? So we could plug -2 in. And if I plug -2 in, I just get -4. So that corresponds to a point, right? -2, -4. So we've got a point, and it's going to be solid or open at -2. Solid's correct. How come? Okay, because the red region, look at that, the red region includes the -2. So we're going to pick a solid endpoint to use at -2, -4. So right there. Okay. What would be another point we could pick? I mean, just a convenient one. It doesn't matter. Like throw one out. What's another x value we could pick here? Does this seem like a reasonable one if I pick -4, for example? That's all right, isn't it? I mean, that's not giving us, I wouldn't want to pick one, like what would be wrong with picking -10? Yeah, it's too big. Like it's way off the graph vertically. We don't want to do something like that. We want to pick one that's relatively convenient, just a practical consideration, not a math consideration, just in terms of just graphing this thing. So if I evaluate my function, if I plug -4 in for x, what do I get for y? -8, right? Does it make sense if I talk about evaluating? Let's just take one quick second here. If I talk about evaluating the function, so f of -2, when you look at the piecewise function, does it make sense that that would be -8? Can somebody tell me how they would look at this big mess of a piecewise function and come up with that same answer? Because you're right, it is -8. And I'm guessing a lot of you guys were looking up here at this equation when you said that, right? Because that's the line we're graphing. How would we look at the piecewise function and get the same answer? What's your thinking on that if I'm inputting a -2? What do you think? There's multiple pieces, so how would we deal with that? How do we know which piece to input -2 into? Okay, yeah, which one does it fit into in the domain, right? Does that make sense? Okay, so if I'm plugging -2 in, you got to ask yourself, which of these domains does that fit into? Well, it's going to be the red one, right? Because -2 is less than or equal to -2. So that whenever you're evaluating a piecewise function, that's always going to be step one. Where do I, which row am I plugging that number into? And then it's easy. Then it's just like a regular evaluation problem. When we know it's row 1, we plug it in. And so we would just get 2 times -2 equals, well, I plugged in -2, I guess. I meant to plug in -4, but you get the idea. 2 times -2 is -4, and that's how we would have gotten our -4. Okay? All right, so then we have 2 points. Now all we have to do is just connect and extend. So I need to grab another point. This is going to be, obviously, this is going to be a closed point because it's inside the interval, right? The only place where we could ever have an open point would be at an endpoint, okay? But ours wasn't in the first case. So -4, we said -8 is right there. And then I would just connect and extend. Do I have? No, I don't. Okay. Oh, okay. Yep. There you go. You're right. I was thinking that was 10. There we go. Okay. And then something like that. Everybody good? All make sense? So there's our first one. Okay. What about the next region? There's our first one. Next region, let's see. So that's the blue region, right? Where x is greater than -2 and less than 4. So here's our blue region. Again, we just need 2 points in the blue region. Which 2 points should I definitely choose this time? -2 and 4, right? I want the boundaries. I want to know, where is this thing starting and ending? So let's try -2. If I plug -2 into the function, into the blue function, and now in the blue region, we've got this function, right? We've got the line y equals -1 minus x. So if I'm plugging in -2, what do I get? Yeah, 1, isn't it? Good. So -1 minus -2 would give me +1, wouldn't it? So I get that point. Okay, now, is -2 actually included in the blue region? What region is -2 actually in? The red region. Why did we pick -2 again? Because it's a boundary, right? That might seem a little confusing. Technically, I really couldn't plug that in and say it's a part of that region, but I know it's an endpoint, okay? So what kind of an endpoint am I going to use here to communicate that? That it's not technically in that region, but it is the boundary or the endpoint of the blue region? Open, yeah. So at -2, 1, I want an open endpoint. -2, +1, there you go. And then we'll do the same thing you already told me for x equals +4. What's -1 minus 4? -5, okay? So there's my other endpoint. Open or closed? Open. Okay, again, because 4 is actually not included in the blue region. It's just an endpoint. So we say that was 4, -5, okay? There we go, okay? And then all of the infinite points that actually are included in the blue region would just be the ones on that line segment that connect the endpoints, right? Okay, so we get that. Okay, give me 1 to 5 on that. How are we doing? Is that all making sense? Okay, then the last part, green region, that's every place greater than or equal to 4. Throw out 1 endpoint for sure, or 1 point for sure. I kind of gave it away. We want to use 4. Is 4 included in the green region? It is, so we're going to end up having to have a closed endpoint. If I plug 4 into my function, what's the output? In fact, what's the output always going to be? -3. Doesn't even matter what the input is. The output is -3. What kind of line do you expect the green line to be? Straight. Well, they're all straight. What do you mean by straight, though? Every line's straight. What is it? Vertical? Agree with that? If the y value is always -3, okay, that makes it horizontal, right? Because the y value stays the same, regardless of what x value we put in. So then we would get, for example, the point 4, -3, and really picking another point is It's almost kind of unnecessary here, isn't it? We know we've got one at 4, -3. It doesn't matter what other x value I pick. The y value is guaranteed to be -3. So take your pick. We'll just throw in 8, which is at the end. Not that it matters. End of our graph, at least. Okay, tell me about open or closed on those points. Closed. Okay, both are closed. Good. Yeah, -3. Okay, so we got a point there we graphed and a point there. And then it just goes forever to the right, doesn't it? So that's our graph. Okay, there's all 3 pieces. So later on, when we start talking about, we'll mention these words this year, but when we get into calculus, we'll talk a lot about this stuff. We would say that this piecewise function is discontinuous at -2 and at +4, because those are places when I graph the function where I would have to pick my pen off the board. So any place where we have to pick our pen off the board to graph something or off the paper, those are discontinuities. Okay, again, that's really not an algebra 2 issue so much, but a big issue in calculus. Next step, domain and range. Okay, so remind me, now we haven't talked a lot about domain and range yet, but I want to just start thinking about it now. We're going to look at that in more detail. Let's see. Well, you guys talked a little bit about this, didn't you? Because that was stuff when I was gone. You guys watched a video about that, correct? Didn't you? Yeah. Okay. So we have. So I wasn't here, so I'm not remembering that right. But you guys have technically seen this stuff. So help me out with that. Domain and range. What is the domain? How do you define that? The set of all what? X values, or just in general input values. Usually X, because that's usually our input, but it doesn't have to be. Whatever our input variable is, that's the domain, the set of all those values. So looking at this graph here, what is the set of all input values? All reals, yeah. You're just kind of really asking yourself, okay, which values are excluded, and there aren't any. Every value is included. In other words, if we think about this in terms of the ant again, as the ant is walking along this function, the ant always has solid ground to stand on. There's always an x coordinate for the ant to stand on, right? He's never falls through anything. He's always got a place to stand. So domain, all reals. Okay, the range, what is the range again? Define that. Y values, set of all the y values or the outputs, whatever, usually y, doesn't have to be. So what about the y values? Now that doesn't really look like that is necessarily all reals, does it? Okay, we want to find all the possible y values that the ant could step on. Say it again. Less than 1 is the right answer. Yeah. Okay, does everybody see that? That's a little tougher one to see. Give me 1 to 5 on that. Do we see that that's the... Okay, that's pretty good. I mean, that you guys see that so quickly. One way you can always think about this, I'll just show you something that's kind of a cool thing in math, because again, this isn't so tremendously important now, but in the future, you guys will talk about when you're like in college, you'll talk about projections. Like like for example, you might project, here's an example of a projection. You could take a 3-dimensional space and project that information into 2 dimensions. How in the world you guys have all seen this before, actually. Have you ever seen a situation where 3 dimensions are projected onto a 2-dimensional piece of paper, for example? Yeah, TV. Well, okay, true, but with a TV, you don't really have all the information there. Like a map, exactly, like a topographical map where they've got lines of altitude and stuff. So you actually have the information on there for that 3rd dimension, which is height, even though you're only seeing 2 of the dimensions on the map, right? So something like that. So you'll do projections, more in the future. Here's just kind of an introductory idea about projections. What if I took each of these 3 pieces and projected those onto the y-axis, because that, you guys told me the range is the set of all y values, right? If I took the red piece and projected that onto the y-axis, wouldn't it just look like this? Like this point's going to project over to there, that point right there is going to project over to there and so on. And it would just fill in that whole part of the y-axis, agreed? If I projected it or just squeezed it onto the y-axis. What if I did the same with the blue? Well, the blue is going to have a top value, a maximum value of 1, but it's an open endpoint because 1 actually is not a y value that's included. And then it would go all the way down to whatever that is, -5, but those are already graphs, so I don't even really need to put that open endpoint in there, right? Those are already part of my range. So it's just going to add all the pieces, all the y values that are greater than -4 and less than 1. And then the green range, if I project that, well, that's already a point that's in the range also, so it doesn't really contribute anything new. Okay, make sense? All right, so then our range, we would say as if I'm using interval or an inequality, I would say y is less than 1. Using interval notation, what would that look like? With what kind of parentheses? There we go. Perfect. Okay, good. All right, you're getting this stuff really quickly. That's good. That's good. Okay, let's see if we can just zip through one of these. Well, I don't know. What do you think? Do you want to go through another one of these? One more, maybe good idea? Yeah, let's go through one more. Okay, what about one like this then? Let's just kind of go through the steps. Go through the steps here. What's my first step, at least in my mind, that I'm going to do? Yeah, I want to break it into regions. Where are my boundaries going to be, the vertical lines? 0 and 6. Okay. So there and there. Okay. And then based on those boundaries, we'll split it up into regions, right? Now, and again, you guys don't have the luxury of color coding this, but up here we do. So here's going to be the red region. That's the top, essentially that's the top pieces region. Here's the middle pieces region, which is blue for us, and then the bottom pieces region, which is green. We need to pick some convenient points. So what would points be? Pick a couple for me in the top region. 0 would definitely be a good one. If I plug 0 in for x, what do I get for y? 0, right? Yeah, exactly. Exactly. Because the red, the top equation is y equals -3x. So -3 times 0 is 0. Open or closed endpoint? Open. Yep. So we get an open endpoint at the origin. Give me another convenient point. -2, -1. You pick. I mean, any of those would be fine. So how about -2? That looks good. We got 2 ordered pairs. -2, 6, open or closed? So what would it be? Definitely closed, right? It doesn't even make sense to almost ask that question because that's a point that's inside the region. So of course that's a point that's on the line, right? Open endpoints or open points would only make sense as possibly at an endpoint, but that's it, right? So then -2, 6. Whoops. That gives us point -2, 1, 2, 3, 4, 5, 6 right there. Okay. And I could just graph this guy. Let me see if I go to the next page. Oh, never mind. I can't do that. Okay. So there's my red piece. Blue piece. What would my 2 points be that I'd want to select here? 0 and 6. If I plug 0 in, and let's go ahead and write down the blue equation. Blue equation would be the line y equals -1/2 x minus 1. If I plug 0 in, what do I get? -1. If I plug 6 in, I get -4. Good. So there's my 2 points. What are the endpoints like here? At 0, closed. Okay, so 0, we've got, what was the point again? 0, -1 was closed. 6, -4 is open. Okay. And then I just have to connect those two with a line segment. So there's the graph of the blue piece. Okay, good. Give me thumbs. How we doing? Okay, how about the green piece? Green piece, endpoints, or excuse me, what would my values be? What's one I'd pick for sure? 6. Okay, if I plug 6 in, let's write down the green equation. Y equals x minus 7. If I pick 6, what do I get? -1. What would be another one be? How about 8 would work, right? If I plug 8 in, I just get +1. And what's the nature of the endpoints here? Okay, open, and then there really isn't another endpoint. Good, so open at 6 and just a regular point at 8. Okay. So there's my graph. Looks good. Let's get domain and range now. What's my domain this time? Is it? Is it all reals? Okay, everything except 6. Yeah, right. There is a place where the ant can't stand because I have both of the boundaries at 6 in the blue region and the green region are open endpoints, right? Neither one of them is included. So how do I say that? Well, the domain, there's a couple ways I could do this. If I want to write this using an inequality, the easiest way, honestly, is just to say x is not equal to 6. Right? If I say that, that implies that everything else is fine, but x cannot equal 6. That's the way we would probably write it in calculus. Now, if they really want you to write that using an inequality, where I can't just say a not equal sign, how would I have to write that as an inequality then? Yeah, either x is going to be less than 6 or x is going to be greater than 6. It can be any other thing, but it just can't be 6, right? So that's the other possibility. X is less than 6 or x is greater than 6. How would I say that with interval notation? Oh, by the way, on the last one, we didn't do this on the last one, but we could have. Oh, what happened here? There we go. How could we have said all reals with interval notation? Negative infinity to positive infinity, because it would have been the entire axis. So the left endpoint would have been clear out at negative infinity, right point at positive infinity. So yeah, we could have said that. Okay, so how about this? Did I delete something? Or? No, I think you have to go forward. Like not one, but two. Go one more? Yeah. Oh, there we go. Okay. So what would the domain be here then if I wrote that with intervals? How would I say x is less than 6 with intervals? With parentheses on both. Good, because I'm not including either of those endpoints. What's my, oh, there we go. What's my or like, Bree? Like a U. There you go. Okay, so I got a U. And then over here, I've got 6 comma infinity with parentheses. Good. Okay. How about the range then? We haven't dealt with the range yet. So if we project all this stuff onto the y-axis, everybody agree we're going to get from the red piece, we're going to get this, right? How about from the blue piece? What's that going to look like as a line segment on the y-axis? Okay, it's going to go from -1 down to -4. What kinds of endpoints on that one? Okay, open on the bottom, closed on the top at -1. Everybody agree? So it's going to look like that. Here, let me color in the middle just so we can see. Oops. Like that, right? And then finally, the green one, what does that do? Okay, open one at -1, but whoops, there's already, that point's already a y value that's included, right? That's already part of our range. Everybody agree? So that open one doesn't really contribute anything. There's already a closed endpoint there. And then what does it do? What does it effectively do to our range? Oh, yeah, good. It's going to fill in everything above that, isn't it? Right. If I superimpose all these points, that one right there is going to fill in that open endpoint, and then the rest of it just overlaps, doesn't it? So that's our range. Okay, so how would I say the range as an inequality? Okay, what's greater than -4? Y is good. Say that as as interval. Whoops. -4, comma, infinity, and I'd need parentheses, right? Okay, good. All right, let's turn this around. So now I'm giving you a function, and I'd like you to tell me the domain. I want you to write the piecewise function, right? So you can also say that as give the rule, meaning what are the equations for the individual pieces, or just write the piecewise function and give the domain and range. So let's kind of color code this one too. How about if we make this first one red? Okay, how am I going to write that red piece? That's going to need a row. It does, yeah. Here, let me make that more clear too. Blue one has an open endpoint, so there. That's a little better maybe, huh? So the red piece, how would I write that? Okay, so let's start with the domain. That's a good idea. Let's scoot over to the right, and for the red piece, let's start with the domain. The domain is x is less than or equal to 0. And I've got to come up with the equation of this line. What is it? -x. Yeah, and we can, pretty easy here, right? We can see that because we can see the y-intercept. Okay, what if that boundary were someplace more inconvenient? We already know the answer. It's y equals -x. But what if the boundary, just hypothetically, were like here instead? So I wasn't really, I didn't have that part of the graph. What could I do? Okay, I just need, right, exactly. I would just need to come up with a point and a slope that I could plug into my new point slope formula, right? So I would pick two convenient points. Like, for example, I could pick, maybe this point right here with coordinates -2, -2, and this point right here with coordinates -3, -3. I could calculate a slope. -2 minus -3 over -2 minus -3 equals 1. So I got my slope. I could take the coordinates of a point and plug those into slope intercept, right? So y minus -2 equals 1 times x minus -2, right? And I would just get y plus 2 equals x plus 2, subtract 2 from both sides, and get, we got -x. That shouldn't have been that, should it? I don't know. You guys probably didn't say that. I don't know why I wrote it down. What is the slope of this line? 1. So then what should that equation be? Just plain x, yeah. Right. Okay, give me thumbs on all that stuff we just did. So if it's not convenient, just use point slope. Find 2 points, calculate a slope, use point slope. Okay, what about the blue one? What's the domain? What's the blue domain? What's that doing? Oh, is it doing something weird here? There we go. What's the domain again? Sorry. Greater than 2, the domain for the blue piece? Greater than 0, right? Remember, don't get, it's easy to that's a, just a, everybody makes that mistake from time to time. But remember, domain, you're thinking about the x values, right? So it's going to be x is greater than 0. And what's the equation of that horizontal line? Y equals what? Yeah, so what goes there? 2. Okay, give me thumbs. Okay, questions? Any questions? I mean, at this point, probably it's a matter of just getting some practice in to get your questions answered. Let's look at one more thing here. How do you do this on Desmos? Okay, do you really have to do it on Desmos? Not very often, but you can. You can. I want to show you how. So there's a scheme for doing this, and I thought I built something better than that. Just give me 1 second here. Let me peek ahead here. Yeah, okay, here it is. So on Desmos, here's the way Desmos wants you to input this. So you can't really build a function that looks like this conveniently in Desmos, where you've got 3 separate rows when you're inputting something. In Desmos, you kind of just have 1 row per function. So what you do is you break it into the pieces and you input them this way. So again, we'll color code these. We'll make the top one red. We'll make the middle one blue. And the bottom one green for our purposes. And then here's how that would translate. In Desmos, you would open up a set of, you would just do f of x equals, you're going to open up a set of script brackets, because this is a script bracket, right? I guess that's why they use the script brackets. And then you're going to put that stuff in, but they kind of go backwards. Like for the red piece, they want the domain first. So the domain would be what? X is less than or equal to -2. Then separating the domain for one of the pieces, so one of the rows, separating the domain from the actual equation is a colon, right? So you'd put a colon there, followed by the equation for the first piece, which is what? 2x. Okay, so then I've got my 2x. When I separate the individual pieces, I put a comma to separate the individual pieces. So what would come next, do you think, in blue? Okay. Yeah, and the nice thing about Desmos is we can write this compound inequality out so it looks exactly like that. That's convenient. So -2 less than x less than symbol 4. What comes next? Colon. And then what? There you go. -1 minus x. Now what? Comma. Good. To separate. There you go. X is greater than or equal to 4 colon -3. Okay, and then don't forget at the end, and I think it'll already be there. I think when you open up, when you type in this first script bracket, it automatically puts a second one there. So you can't really forget that, but that's what it should look like. Okay, let's do this once, just so you can, because I want to show you a couple little tricks in Desmos. It's not that big a deal. Okay, I think it's right here. Okay, so let's go through this process. You guys told me what to write, but just for grins here, why don't you tell me again? Good practice. What do I write first? F of x equals, okay, but what do I put first? Script bracket, there you go. Notice it opens up two of them. So now I've got top domain, which was x is less than or equal to 2, right? How do I type that now? I can go down and I could pick out right there, there's a button for it, but I always prefer, it's quicker and easier to just use the keyboard if you can. How can I put in less than or equals to in Desmos, do you suppose? All I do is type less than and then an equal sign, and it knows to lump those together. It's pretty smart. So less than or equal to -2 colon 2x, comma, good, -2 is less than x less than 4, colon, -1 minus x, good. Next, comma, okay, good, x is greater than, equal to, combines them, 4, colon, -3. Okay, let's see how that looks. Okay, that's pretty good, but that's not as good as our graph. What's it missing? Yeah, the endpoints, right? So what's bad about this, the weakness of Desmos is it doesn't really tell you where the closed endpoints are. There's a way to fix this though. In Desmos, this is what I always tell students to do. So you get a little better picture. I can go down here and just open up a couple ordered pairs. So if I open up an ordered pair, what's one X value I'm interested in knowing about? -2. So I'm going to open up the ordered pair, which I'll tell you all about tomorrow.